for those of you who don't know, last year I discussed this computational course in QCD that I've written. 5 lectures. It sort of builds up from with examples from my own package grid, how you highlighting how you implement the algorithm. It builds up sort of the algorithmic structures of lattice field theory as such. So we implement finite difference operators that represent our differential equations like the Dirac operator, etc., with different discretization schemes. These stencils, I illustrated with the example of just implementing Laplacian, then a gauged Laplacian, then you can apply polynomials of that Laplacian, and if you choose a polynomial wisely, you can approximate any function, including the function 1 over x, right? And if that polynomial is valid over the entire eigenspan of the matrix, then you get something that's called an inverter, right? Because you get 1 over lambda, right? And because our Hermitian operator is diagonalizable and so on, the polynomial of it is simply applied eigenvalue by eigenvalue, and if the approximation is good enough, you have a high enough order polynomial, you have a decent inverter. And then it's got Krylov-space solvers where rather than say choosing the optimal Chebyshev approximation, you use data-dependent decisions, and then there's a spectrum that is not. So the Chebyshev will minimize the worst case error over the matrix. That's what these minimax, so variance Chebyshev polynomials give you. The Krylov solver will look at basically the spectrum of your matrix where it's and work harder where the spectrum is denser, because it minimizes a norm to decide how it sets its coefficients, right? So for conjugate gradient, for example, minimizes the error in the A norm of the matrix where A is the matrix. So it goes through that, then it moves on, so it's done in rival solvers, etc., then starts building up HMC, introduces metropolis algorithms, proves the detailed balance condition and so on, that converge in the midpoint distribution, etc. So some overlap with that, but going in a different direction because it goes in the HMC direction. And then goes into how do you assemble these things into the invert propagators and assemble endpoint functions, etc., and assemble electronic form factors or whatever, as an example. So that is there as background resource. But we've been asked by the program manager, I think, I can't remember when the emphasis Jeremy wanted was more HPC and co-design focus, right?
This is the FOA. Yeah.
Yeah.
Then our advisory committee suggests we also educate students a little bit more on the hardware, what you need to do, special software for the hardware.
So what I've done is I've reassembled much of the same material, but tried to put a stronger hardware emphasis on this. And also, last year you saw the swan swimming calmly over the water. You can see the legs paddling, and what happens when it doesn't work. So this year, the unvarnished truth of the things we have found and had to fix, and you would wonder why are we as theorists the ones who are having to find and fix these for the computing centers, for the vendors, but I've sat in a system and whenever a computer anywhere in the world doesn't work, apparently I am the person who gets parachuted in. Okay, so some resources. The Feynman lectures in computation are fantastic. Being Feynman, he builds up sort of almost from the atomistic level up. So he talks, introduces transistors, flip-flops, how you get registers that latch their input value, and every rising clock edge, hold it till the next clock cycle and repeat, etc. And he built up how to build, arithmetic units and so on. And by the time he hits his final lecture, he lays the foundation of all quantum computing, right? So it's very Feynman-esque. Then computer architecture, Hennessy and Patterson, in my view, so this computer architecture quantitative approach, in my view, the Bible of computer architecture. These are the guys who invented RISC chips, Hennessy and Patterson. I have my examples, etc. Tony Kennedy for real pedagogical introduction to the algorithms of lattice. Tony Kennedy is, of course, brilliant, and the book by Sad is wonderful if you could take a limited set of resources to look at. So where are we now? Well, rightly or wrongly, of the large-scale computing systems in the US, we have 3 current systems, all of which have 3 different architectures, none of which support the same set of software interfaces. And of course, CPU computing is not going away. So there is a diversity of targets which has to be accommodated by our codes. They're also quite complicated. So this is just a couple of examples. you have these multi-GPU nodes, which means, of course, we as scientists are having to delve down into the things that games programmers have to do, right? And we have no choice about that, right? And really, there is no choice about that because the way computing electronics has gone, highly parallel, organized swarms of units is the way that you have to go. And these are de facto the only real way to exploit these in a way that's efficient. So you have multiple GPU nodes. You also see links between the GPUs. So there are multiple networks in the system which are different. If you're going to write code that's really optimized, you will have to recognize the fact that the networks are hierarchical. There are intranode networks which are different from inter-node networks. And you will actually deal with the transport distinctly. And if you're, I'll give examples. If you're wise, you will also make sure that you map the geometry of our problem to that hierarchical network so that you maximize the amount of intranode bandwidth that you're using and minimize the amount of internode bandwidth you're using, because the intranode is a heck of a lot faster than the internode, right? So you have to recognize the hierarchy of the hardware. So it's a great example of what Henderson pattern on into about spatial locality of problems, right? Because we have a spatial locality in physics, right? Physics is necessarily local. You want to try and map to the hardware in a way where the locality of the physics problem is mapped onto the locality of the networks, right? Okay, so we have these hierarchical networks. You then, of course, end up having to deal with things like opening of memory windows between the GPUs to get permission from writing to each other's memory, etc. Which is, of course, a complexity. And I'll just point out the really nice the really nice sensible sort of nonsense you have to deal with here. That the sanity that NUMA domain, this is rather small, but NUMA domain 0 of course has to have GPUs 4 and 5. NUMA domain 1, of course, has to have GPUs 2 and 3, right? The numbering here is completely insane. You have to recognize that in order to exploit the locality and get the geometry correct so that you can structure these 8 GPU identities as, say, a well-formed 2-cubed cube, you have to understand this mapping, right? And if you get it wrong, you lose performance by a factor of 100, right? So, yeah. Okay, so all major US supercomputers are GPU accelerated, plus many or most recent EU installations. As I said, software incompatible platforms. To use them, the code must be highly parallel, regular, lots of work items executing exactly the same software path. And that's because there's a single instruction fetch. One of these streaming multiprocessors inside the GPU, it fetches a single instruction and will order the operations of about 32, what they call threads. I wouldn't necessarily call them threads, but 32 SIMD lanes. And if they are doing different things from each other, say 32 different things, they would have to fetch 32 different instructions instead of one, right? So you immediately, if you get what they call thread divergence, you lose a factor of 32 performance, right? So you need regularity. Further, you need spatial locality. So the data must be structured and laid out to create locality of access so that when this unit inside the swarm of 32 accesses one word of data, the next unit along accesses the next word along, etc., 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 so that they all both do the same operation at the same time, but also to do the same operation on consecutive memory locations at the same time. So that's a form of vectorization, albeit it's a little bit hidden from the programming interface for this, what they call this SIMT, single instruction multiple thread model. Okay, so that's the illusion that software interface is complicated so little. I'm referring specifically to what they call the SIMT model for programming GPUs. Native GPU APIs are C++ family, so CUDA, HIP, SYCL are all C++ interfaces. There are huge factors of performance will be lost if algorithms and software do not face these facts, right? So basically you have to adapt the code to this. Not all algorithms will naturally suit GPUs, like stuff, right? But if the internal abstraction is defined right, forcing between them is easy. So I had the mission when I think 2018-19, I did the CUDA port of Grid, then I, of course, abstracted the interfaces with macro as accelerator for, I'm not going to pollute my code with proprietary nonsense, right? I'll write a macro that contains the proprietary nonsense and abstract my code to my own internal API. Then I managed to do both the HIP and SIG. I got that abstraction sufficiently close to correct that I was able to do the HIP and SIGL ports of grid in the same day, right? It wasn't optimal straight away out of the box, but it was both of them in one day, right? Okay, this is just a bit of a electronic. This is from my 2016 latest talk, but the point is, if you think of the RC, we all know RC capacitors discharging and all of that, right? If you take the resistance and capacitance of infinitely semi-infinite cylindrical rod, right, in a dielectric medium, right? The resistance is L over pi r squared. You're going to know the capacitance by you can apply Gauss's law, get the electric field, and then integrate that, get the potential, and then you have the capacitance. What you see is that the RC time constant is essentially proportional to L squared over R squared up to logarithmic terms. That means that the aspect ratio of a wire dictates how long, the time constant that dictates how long it takes to charge or discharge. So if you flip from a 0 to a 1 or a 1 to a 0, this time constant tells you how fast that wire will transition at the other end, right? So, and the point is, it depends only on the ratio of the length to the radius. If you're doing your semiconductor trip shrinky thing where you cut every dimension by a factor of 2, basically the wire delay stays fixed, right? And the comment here, and the only things you can really change here are either the resistivity or the dielectric constant, right? Hence low K dielectric chips and copper interconnect. So they've pushed the buttons that they can in terms of the material science to get the wire delay as low as possible. And certainly back 2012, when I wrote this on 45 nanometer, my slowest timing path was 50% wire delay and 50% transistors, right? Switching. And if you shrink further and the transistors get better, no matter how good the transistors get, you can't clock it faster, right? Unless you change the aspect ratio, right? So the result of this, so if you have long, skinny wires, right, they will be slow, right? So the only way you can possibly wire an 8 billion transistor chip is by having locally highly interconnected, not broad, thin wires, and then long haul buses where the wires are broad, right? And you can only have relatively few wires that are broad on a given layer because they're big and they're taking a lot of area. So that means you have to have locally connected pools that you can wire and make a sensible timing, and then have these communicating with each other, which drives you to multi-core design, however you structure it, right? And similarly, there's this thing called high bandwidth memory, where again, they can stack chips and then put kind of like the medieval Europeans were really nasty to each other and had these things called Iron Maidens, where they would put spikes through people, right? They've got spikes rising through a tower of chips. And the whole point of that is you have then nice aspect ratio for the transmission. You can clock the data in and out the chip stacks efficiently, right? So, high bit rates. And that gives rise actually to current modern GPUs with high bandwidth memory, et cetera, et cetera, et cetera. Okay, and I guess one example, and this is actually the case I would make for maybe in the future we'll hit 3D interconnect or 3D chips, 3D logic chips, not just 3D memory chips, right? If you can cool it, right? But you can always cool things in some sense because we can put metal through things and metal conducts, right? So, with scupper types of chips that with data, right? Sure, we can conduct heat out in some way with a central mechanical solution. And the example I use is, living in Long Island, you learn that the mean distance you drive in a one-dimensional system really sucks. Right? 2 dimensions is better. 3 dimensions, the mean distance you would have to drive would be a lot smaller again, right? And here, potentially the way to keep RC delay or wire delay long term is to go to 3D logic, right? Because you will reduce the mean wire length in a chip and not be stuck in these planar structures. And planar structures are a lot better than one-dimensional structures I have discovered. Right. Okay, so these are difficult to program. I said basic physics, right? I've explained basic physics. That's how you end up with these 3D wires and then high density interposers of some type connecting multi-chip modules. Yeah, and that drives us to this kind of system integration. So I'm trying, obviously I can't compress all of computer architecture science into like 20-minute waffling, right? But this is my best attempt, right? So fundamentally, a CPU is a finite state machine. It has a current state, or it has to be logically equivalent to a finite state machine. You of course stretch it out and have it do multiple things at the same time. But I've worked with Intel, some of you know. Intel has an in-order reference state description, right? That when they run, they collect these traces and compare what they get out from their out-of-order, aggressive, super pipeline, mega this, mega that thing to what would happen if they ran it with the slow, simple instruction fetch, decode, blah, blah, blah. It's the definition of what's correct. And there's a reference against which everything else is regressed, right? So when it's a finite state machine, it goes through instruction fetch, decode. When it decodes, it decides which execution unit has to do, is this a load instruction? Is this an arithmetic instruction? The state is augmented with something called a register file, which contains some number of words of data, right? Typically something like 32 integer registers, 32 floating point or vector floating point registers or something like that. It goes through some series of stages. So if you're going to do, I'm giving the classic load, store, operate division that Henderson and Patterson introduced, where you can either detect it's a loads from memory, sticks it in the register file in a specific destination register. The register, you can think of like a scratch pad that are local. And then it can say, take register 0 and register 3, add them together and stick the result to register 7, things like that, right? So an exercise which would be entertaining for people to do is get an assistant that has GDB, not a Mac. Mac doesn't actually use GDB. It calls it GDB, but it's really LLV and LLDB underneath. Run GDB, set a breakpoint in main, type layout ASM, and you will see all of these registers. That is the definition of what is the state of this finite state machine, right? It has something called a program counter, which is the current instruction pointer. By default, it fetches one instruction, increments the program counter, fetches, does whatever it does for that. If the instruction is a branch, it then has to change the program counter to whatever the branch says it is now going to. But basically, it's just you think of the program as a sequence of consecutive words. These words contain codes. Subfields of the words. Some number of bits of words are the primary opcode. Some bits of the words are the secondary opcode. The primary opcode will say which unit it goes to. The secondary opcode will say, this is an add, this is a bud, whatever. It has other operands like 7 for register 7, whatever, right? Okay, so this is the processor state, but you can think of it as a finite state machine. So doing various steps, typically doing these sequentially for each instruction. You go through a process where one cycle is in the instruction fetch stage, the next cycle is in the decode stage, the next cycle is in the whatever state, right? That is intrinsically inefficient because it's waiting many cycles to do one thing. So what they typically do is what they call pipelining, which is analogous to, if you want to put out a blazing fire, you don't run and fetch one bucket, you get, 100 people, put them in a line and 100 buckets, and you start passing them down the line and then you're putting out the fire much faster. That's a process called pipeline, right? And the idea is that you have the instruction fetch portion fetching an instruction and then handing over that to the decode and going and fetching the next instruction before the whole process is finished. That, of course, means that if the program flow decides to do something else and it's fetched the wrong instruction, you have to cancel out and remove stuff, right? And potentially, if you have an instruction that's clearly dependent on an earlier instruction, right, you have to wait until the earlier instruction has completed before you can execute the dependent instruction. That's called a pipeline stall. So, yeah. So modern CPUs will, if even complete independent instructions out of order, say, well, this one's independent of that, and I've got the input values for this one's already here. I can execute it now, even though the earlier instruction hasn't completed, but I know they were independent. So it's tracking what they're called scoreboarding, tracking all of these dependencies and able to do different things at the same time. So one of the examples I have for this, one of the reasons, the day I decided, I used to write my own compiler backend for these RISC chips, and I got order of magnitude faster than the compiler. The day I decided to write Grid, the guys actually who wrote Sickle, but this way back 2014, they were a compiler company in Edinburgh. They told me what the games guys who are writing the Grand Theft Auto, the Rockstar, are doing, and they're doing their cross products by using Pauli matrices and using the epsilon IJK structure constants, right? And that gives them a cross product, right? And he described the way they write their code. And I thought, oh, I'll try that. And I did an SU3. Instead, they write little vector classes that are complex vectors and stuff like that. So I tried this, wrote it, and discovered that. So the problem, the obvious matrix multiplier where you have A, I, J, J, K summed over J, right? Each add you're doing multiplying and add. The result of when you add the first two together, you depend on the results of the two multiplies. So you should wait for a pipeline stall before you can add those two results together, right? There should be 5 or 6 cycles. The Xeon, the Skylake chip I was looking at was looking over the first loop, stalling these, and then if you're doing SU3 times SU3, you've got row column products, right? It was then going to the next row and starting the first instruction of the next row while the first row was still in flight. And it unrolled the entire thing and reordered loops, right, in hardware, right, and got basically peak, right? So I thought, oh, this works, right? I can stop writing my own compiler and I can rely on these kinds of chips being able to run efficient code, right? So that's out of order CPUs. And of course, the biggest stalls happen when waiting for the result of memory load. So memory latency is typically of order 100 to 150 nanoseconds. These are 2-3 gigahertz chips, right? That can easily be 1,000+ cycles you would have to wait in the case of a miss. And there's all sorts of studies about profiling programs are saying that 1% of the loads are responsible for 90% of the runtime and so on, because these are the ones that miss the caches, etc. And of course, the vendor response to this is throw billions of transistors at bigger caches, typically, right? Which isn't necessarily the most inventive use of the silicon area. Okay, so why GPUs are actually more interesting these days, because they're actually putting more of the effort into the execution of cache sizes and then augmenting that with high-speed memories instead. Okay, so the cache line size, typically 64 bytes, is a unit of granularity transferred. So if you access 1 byte, you get 64, whether you like it or not, right? This optimizes for 2 things. So you retain on chip copies of data, and you have to remember, is this modified, does that have to be written back, etc., etc. They have all these protocols, METI, they call it, modified, exclusively owned, shared, or invalid to handle which core owns which line of data, and to make sure it actually executes the same way as if there wasn't a cache in the first place. The 2 things that this optimizes for are the principle that if I access one element of a data structure, I'm very likely to access the nearby elements of the same data structure. That's what we call spatial locality. Right? So nearby words get accessed together. So by transferring more, make it very likely you get a hit in subsequent loads, which increases performance. The other thing they access is they optimize for, well, if you have a program, and I'll explain or talk shortly if people don't know what a stack is. The local variables in your functions live in something called a stack, right? And as you call up and down functions, you repeatedly scan up and down over the same memory, right? For all the automatic local variables in C, for example, or any language. So the idea then is that you have temporal locality. If you access an address of data, you're very likely to access it again in future, right? That's essentially what caches are optimizing for. So at this point, to try and, I mean, I don't know how understandable all of this is this at the right level or whatever. First of all, feedback. Is this making sense? Yeah. So, I've just sort of told you about questions for the class, discussions. Who knows what a stack is? Right, of course you do. So, what tell us?
Did you? I mean, a stack's a data structure where you can place things. I mean, it's like a stack of plates. You put things in, push things in, and pop them back out.
Yeah, I mean that's
a level of
a stack is like a chain of Lego bricks where you stick data on the end, and then the point is you have a stack pointer, right? And most chips have something architected to stack pointer. Or there's a dedicated register that says this is a stack pointer. When you make a function call, you take whatever is the current stack pointer, your function, the compiler knows when it compiles a function how many variables were in this function. What it does is it subtracts the right number of bytes from the stack pointer to leave space for that function, right? And then uses a frame, they call it a stack frame, the region that's allocated itself on the stack, it can use for its own things. And then once it's finished, it has to put the stack pointer back again. And then the function that called me thinks, oh, the stack pointer's at this location. So basically, every function dereferences relative to the stack pointer, and it's kind of like clean up after yourself. You pull down, you push back up again, and the next guy takes care of his stuff, right? And you're not allowed to the famous Stack Overflow website, right? It's the unique nature of bug where you allocate something in the stack and you accidentally have an index out of range, go off the end of your array, and you pollute someone else's functions data. And then you get all these hideous side effects which are delayed because you have this sort of chain of Lego blocks. And if you go in and trash the Lego block above you and you overwrite some pointer with the points to null or whatever, you then get random writes over the program and the symptom of this is because your function was accessing legal addresses for the program, there's a deferred error, right? And you only find out later in the program. These are some of the most nasty bugs to debug because you get deferred errors. And finding the stray write that caused this is genuinely evil in some cases. It's like Stack Overflow, the name of the website, right? I'll actually give an example later of a uniquely pathological version of MPI, which I mentioned, where I tracked this using GDB or tracked something like this using GDB, where the binary was, the program was essentially committing harakiri on the code sections of the program at runtime, right? And doing all sorts of things to give itself permission to do so, to go and lobotomize the dynamic library tables, which it got wrong, specifically on the ARM architecture. Which is entertaining. Okay, anyway, what's the heap?
Heap is more like random access. You can put your blob of memory anywhere, and you can access it kind of anywhere in the heap at a time. It's a big blob of memory that programs can malloc, right?
Yeah, just well, broadly, you're right. I mean, it's always managed by a routine like malloc, and it writes data structures inside it. Then there's traditionally in Unix, there was a big block of memory, and there was a system called break or more core, which will pull down the heap, right? Nowadays, large allocations get done through something called mmap and prevent something called heap fragmentation because you can give it back to the kernel where you can prevent that. But the classic heap, so basically a heap is memory you get from malloc and things like that, and it's dynamically allocated read. And then there's of course classes of bugging you can have where you trash the internal data structures that malloc uses to bootkeep itself, right? And then you also get deferred errors, right? Which these are really hard to do. I should have written, if you ever hit one of these, I'm trying to give some war stories through this and what you do. If you ever hit one of these, Valgrind is the tool, right? Valgrind emulates your program and tells you did something illegal here, right? And that is something worth remembering. There's a tool called EALGRIND, Valgrind. Okay, Branch, what's a branch?
Like the if statement?
And if the certainly creates a branch, what about a function call? It does. Right. So basically, a branch is any deviation from the linear incrementing of the program counter, right? So that has to involve some form of instruction that specifically says, like what you were going to fetch, redirect here. Then you have various mechanisms for coming back, right? You get things called linkage registers or whatever that know how to get back to where you came from. It depends on the architecture how that's implemented. Why do people try to predict branches? Or why do chips try to predict branches?
I try to avoid them because they hurt performance, but.
I guess the question is, why did they hurt performance?
Well, you have to move your pointer all sorts of different ways, and you can't, like your compiler has to keep different options in memory. Yeah, that's the vague.
Okay, so when you have a pipelined chip, it's very often advancing and fetching the next instruction, decoding it, assuming consecutive execution of instructions. And when it deviates from that, it's done a bunch of work that it has to throw in the bin and cancel, right? And that's called a misprediction, right, for example, right? And what initially people start saying, well, mostly things are in loops. So we predict that backwards branches are taken and forwards branches are not taken, right? And then they started storing ways to cache the history, the branch history tables for each specific address. Do we store, was this taken, was this not taken, and things like that. But basically it's all trying to stop the mispredict penalty where you have to flush the pipeline and start fetching again from scratch, right? And that's why branches sort code, right, typically. Anyone got any idea what virtual memory is? Ryan does. Of course you do. Okay, Ryan, what?
I have a degree in computer science.
Oh, yeah.
Yeah, no, I mean, it's the fact that, when you have an individual program, if you look at it, the operating system presents to you as though you have essentially all of the memory in the world, right? You just have a stack, you have this nice stack, and maybe you have a heap somewhere else, and you have all this linear memory, and it'll pretend as though the operating system tries to make it pretend as though you have all access to all this memory. But in reality, at some stage, this has to actually go onto a physical chip. And also a lot of the addresses, for instance, will be the same between different programs. But then, if I have two different programs that both have their stacks at the same location, how do they know which one is which state stack? And virtual memory is just the translation. I mean, so it's the fact that the operating system will translate that down to a low level, into a physical hardware address and say, like, this is the physical location where this actually is.
So to summarize what Ryan's saying, there's what's called a virtual or fake address space. If you think your address, your pointers map to memory in some way, they don't. There's a translation layer. Whenever you do a load instruction, there's something called a memory management unit that takes the address you think you had and maps that to a physical page number in physical memory. And that goes through some process, which is basically like a glorified lookup table. Right? And that lookup table is unique to the process, so that two different processes could use the same virtual address, but they map to distinct physical addresses, right? But in this way, the advantage of this is that having this translation step is if there exists no mapping, right? So you're accessing the illegal address that the OS didn't give you, that translation step will fail, and you'll get something called a segmentation violation, right? Which is the sig V that we see typically, right? Now, yeah. Anyone want to have a crack? Maybe not Ryan. People know this better than I do, but how does a cache work?
Basically, the idea is main memory is slow, and so you have a small amount of memory right next to the processor that's fast, and it stores what was recently used by the processor with the assumption that that's probably going to get reused.
So when you go to access it, what sort of process do you think the processor has to go through?
So first, there's some sort of lookup table that figures out, does this virtual memory address correspond to something in cache as opposed to main memory? It's some sort of buffer table, I can't remember.
Yeah, so
And then it has
So these are called cache tags.
okay.
So they've got some number of lines and they've got basically the address of what they contain and whether it's valid or not, or what state it's in, right? They're called cache tags, yeah. And these are looked up.
And then there's, if you're then writing to a cache, it'll stay in the cache at some point till that cache line is flushed, and then it has to figure out, was this cache line modified? It needs to be written back to main memory. And if you have a multi-core processor where you have multiple cores trying to access each other's caches, then it's even more complicated.
Yeah. So these are actually, yeah, I could go into a huge amount of detail here. Maybe a coffee, but there's different types of caches. There's write back caches, and most people in the industry follow this thing called MESI, some cache protocol for handling multiple chip coherency. IBM does it completely different. It has write through caches and what I call back invalidate as the coherence protocol. And I got very immersed in that, the Blue Gene project, as you can imagine. But they have different scaling properties and so on. And actually, these two, sticking to MESI, MESI is inherently strongly ordered at the cache line level, no matter how relaxed the architecture is, because you have to have exclusive ownership, and that serializes access and write. This is essentially, I think, killed CPU, multi-core CPU as a valid HPC alternative. What's annoying to me is that IBM had a different architecture that was intrinsically more scalable, but lost attention and Ginny cancelled the project. So regardless, okay, so yeah, I described the SU3 and I described pipelining. Okay, here's one for the room to work. All right, something called Little's law in queuing theory. And the question is, how many 64-byte cache line loads must you be able to support having in flight to saturate 100 gigabytes a second if latency is 100 nanoseconds? And what Little's law says, well, maybe people should think about that. This is a calculable thing, right? You can think if you're going to be returning 100 gigabytes a second, you know in that round trip latency, right, the volume of data you must return to saturate that bandwidth, right? So if you take the latency times the bandwidth product, that tells you the volume of state that has to be in flight if you're getting data continuously at that rate, right? So this Little's law is tremendously useful for analyzing memory performance, interconnect performance, all sorts of things. Wherever you have simply a transactional, send request, get data, send request, get data type queuing situation. And what you see is that you can easily end up, if you were wanting to get 100 gigabytes a second out of a single CPU core, you would have to support something like 150 cache lines in flight, which means you have to, with 32, if you're generating your cache line fetches by having each cache line fetch be triggered by a register load, you suddenly need 150 registers, right? And they don't have that many, right? So this actually dictates one of two things. Either you support a prefetch and a very, very deep either software or hardware prefetch where you can generate many requests independent of the load sequence of the chip, right? So you don't couple the register filling to the fetching from memory. You have a decoupled architecture, we call them. Or you have a huge number of registers, and even then it's kind of hard with a single program with dependencies to generate that number of pending loads. So you generate a huge number of registers and a huge number of separate threads of execution that don't have dependencies between each other to generate 150 pending loads. That second solution is essentially what you call a GPU, right? And it's designed around having high levels of memory parallelism exposed to get lots of pending loads and deep queues, and then you can get this kind of mechanism for generating a high sustainable memory bandwidth. Okay, so just to show you these things are fairly complicated, I'm just showing the memory hierarchy of AMD EPYC. So this is the Genoa I believe that went in. So Tim's girlfriend was in the room somewhere earlier anyway. This is system that's just gone into Fermilab. There are 8 die. These are essentially 8 times 8. Each of these is effectively very, very close to what I would think of as a 8-core laptop chip. And they've got a multi-die module with each die has L2s, a shared L3, but then coherence between all of these, all connected to a base I/O die that talks to the memory, right? So you can see this is actually pretty complicated, and you get all sorts of effects if you're exchanging data between threads in the same die or between different die and things like that. And we've seen all sorts of issues with Frontier related to this. And then in response to the comment about what's this, a CPU is a finite state machine, I just on my laptop, this is ARM, so there's these are the architected ARM registers that I printed out. State just did the right whole bar to find out what's state. This really is what would represent the state of a finite state machine. If you are an operating system and you want to task switch and you want to interrupt one process and start another process or etc., this is the thing that you have to save in order to reload the processor's state to start execution again when you come back, right, to that process. Start it going again, and you get program counter that you execute full instruction and so on, interrupted it. Okay, so what is a GPU? So between CPU and GPU, SIMD versus SIMT is the main programming model difference. The GPU premise is to provide hardware for executing 3D, or actually I would say 6D loops, but sorry, Ryan, you're going to kick me after this. The computer scientists tend not to like to think about more than 3 dimensions, so they take their inner dimensions and their outer dimensions and stick them all together into one bigger dimension and call it the joint thing X, and the joint thing Y and the joint thing Z, because I don't like W, S, and T. So in other words, to translate that, when you read the marketing blurb, here are things about thread index and block index. The thread index has an X, Y, and Z, and the block index has an X, Y, and Z. And then say the total X is the thread index plus thread size times block index dot X, right? They combine the X, Y, and Z of one with the X, Y, and Z of the other to make a fused X and a fused Y and a fused Z. That's completely unnecessary. You could just think about it as the intrinsic primitive is a 6D loop, right? I can use any of these for integer ranges for any combination, and folding it down to only 3D is just a choice. So, and then the idea is that what you do is you write for each of these hardware units that you have, each of these single instruction controlled hardware execution threads, you are given access to a tuple that says what is the coordinate in this 6D system. And then the hardware unit has to figure out, the code that you write has to figure out what am I supposed to do for this particular work item, right? So the looping over 6D nested loops is done by the hardware, and you're given your entry point is you are work item X equals blah, Y equals blah, Z equals blah, do your stuff, right? You need to write code to do stuff for one iteration of that loop, right? That's what you call a CUDA kernel at that point. Okay, so loop iterations that are close by can communicate with each other. In other words, you have this thing called shared memory that lives within the single multiprocessor or execution block of the chip. So you can think of the GPU being composed of things I would call cores. NVIDIA doesn't. NVIDIA calls it streaming multiprocessors because they all get called a SIMD lane a core. So, and Hennessy and Patterson reason the latest version of Hennessy Patterson has a language mapping table between NVIDIA's peak and what they call computer science language, right? So what NVIDIA calls a core is what I would call a SIMD lane, right? What NVIDIA calls a streaming multiprocessor is what I would call a core, right? Etc. Right? So a core has a single independent stream of instruction fetch, right? It's the basic thing. Okay, so and they have this shared memory, which is like a local scratch pad. And the advantage of the shared memory is you can randomly transpose the way you're accessing it. So you can access it by row or by column efficiently. And that allows you to load in with the coalesced ordering memory, put it into the shared memory, and then you can retranspose and access it with a different ordering from the threads in a second phase, right, which allows you to do things like efficient matrix transpose and so on, combinations, for example. So it's useful for changing the order of layout while still getting good vectorized loading from the memory at all times. Okay, so basically, whereas by default CPU vectorization, you have these vector registers and load the entire vector register, right? And these automatically are contiguous, and they actually say you have to be aligned on power of 2 boundaries for the accesses, right? Whereas the GPU is kind of what I call hidden vectorization, right? And in many ways, SIMT makes the vectorize easier and more automatic, but you need to get your head around what's happening and penetrate some jargon to, I think, truly understand it. So the SIMD or CPU model, you have a single instruction fetch, you have single address integer variables, right? So there's one stack pointer, right? You have vector floating point variables. Typically, these are what people call the AVX, AVX 512, whatever, all these jargon instruction sets people design. There's ones for ARM, there's ones for Intel, there's ones, all sorts of types. These access CPU memory and require aligned contiguous load stores of entire vectors. Aligned vector operations are cumbersome. Grid, in a clever way, which I could explain offline, but I'm not going to hear. Actually, I will. So there's an idea dating back to the connection machine, and I love this because Feynman worked in the connection machine design, right? There's a wonderful essay by Danny Hillis saying Feynman's son was doing a PhD in MIT, and Feynman came along in the summer and said, right, give me a soldering iron, I want to work on this project. Like he famously in the Apple Think Different campaign, the t-shirt Feynman was wearing was the connection machine t-shirt, not an Apple t-shirt. So Feynman, so the idea of the connection machine, one of the tricks of the connection machine was it was a SIMD machine, and in order to cover memory latency, they said because there's necessarily single instruction multiple data, but what they did was they actually broke the memory into multiple memory banks, and when you executed an instruction, they actually did the instruction 4 times, one in each memory bank with the same addresses, and they mapped their arrays so that they would all, and you would say how to map it to the hardware, these hypercube hardware, so that one of your array indices would be striped across this dimension. You call out which dimensions of your arrays were striped across these, and then it had the constraint that you could only do data parallel operations between arrays that were striped in the same way as each other, and therefore the operations were automatically local to a memory bank and never crossed between memory banks, unless you did something called the C-shift, right? And the C-shift is something that people who use Grid and use Chroma will recognize, but it's inspired by the connection machine. And the point here is that one of the tricks of the connection machine was to use the striping between different memory banks to automatically get SIMD parallelism in a neat way. Instead of making this bit that distinguishes the memory banks a high order bit, I make it a low order bit, which is a consecutive vector index in Grid, but also use the same striping technique the connection machine used in order to create automatic, contiguous, aligned operations, except for inside the C-shift, right? So, yeah. And that translation, so what I do in Grid is I say, if I take the layout on one node and pretend there are more, and the connection machine called these each cell or each what would be each work item could be called a virtual node, right? I take the NPI node we have and pretend we've got more NPI nodes than we actually have. So I say, imagine a square, divide it into 4 quadrants. I then interleave one word from each quadrant with respect to each other. And I'm using translational symmetry because if I reference the neighbor of one item in the first quadrant, the other guys at the same instant will have to reference the corresponding neighbor within their quadrant. So by interleaving them, I guarantee that the vector comprising 4 quadrants neighbor contains the same neighbors relative to each of them. So you can just do a vector operation and have automatic 100% SIMD efficiency, which is obviously useful, except for when you start doing shifts, right? And there you have faces to gather and so on, but that suppresses the non-SIMD overheads by the surface to volume ratio, which is obviously good. Okay, so CPUs, the SIMD or GPU model, a GPU streaming multiprocessor, or what I would call a core, fetches a single instruction. That instruction may or may not apply to every SIMD lane. They have things called a mask register. So if some threads say if and some threads say else, it's worse than just the cost of a branch misprediction here, a pipeline stall flush. It actually, if the 32 threads, CUDA threads, controlled by the same instruction fetch are all doing different things, for each thread to make progress by one instruction, you have to execute 32 instructions, right? So you lose a factor of 32 if you don't have the threads working, doing the same thing at the same time, which is why we need these regular problems for GPUs to be efficient. Then it also is implicitly vectorizing. So if you do a load, you get a fast load where if all threads controlled by this instruction say load, and they all access consecutive elements of data. Actually, it's more flexible than that. If they all access the same cache line of data at the same time as each other, a single cycle returns the right data to all the threads, right? Otherwise, if they're all accessing different addresses to each other, and they have their address registers are independent here, so they can all be different addresses to each other in principle, depending on how you write your program. It's data dependent. So the GPU will look at the data, they essentially say, right, I have to fetch the first guy's address. Can anyone else use this? And if they do, they go, oh great, we're done, right? If they all have different addresses, then we'll have to fetch however many different addresses there are amongst all of these registers before it completes that load instruction. So you can see that this process, by default, is a scattered load, or a gathered load, I should say. But the hardware will detect and accelerate the case where they're all hitting the same address and the same cache line address, and then they're all resolved in one cycle. That process is called read coalescing, right? Hardware detection of them all accessing consecutive data or spatially located data, get read coalescing, which goes 32 times faster than non-coalesced, right? Or that order of magnitude anyway. So in particular, the stack pointers are normal address, normal integer registers as well, right? So they all have different stacks, but they have special addressing modes, I believe, for when you do stack access. So you have local memory and global memory, right? When I think the thing, I'm not absolutely sure, but I think the thing is arranging that their stacks and their virtual address are offset relative to each other. And then what it does is it shuffles around bits that they all think they've got their own private stack, but there's a high order power of 2 aligned offset between them. And then in physical memory, it takes the bits and rearranges them and makes sure that in physical memory, they're actually consecutive when you going across a thread index. So they've reordered the meaning of the address bits between their virtual space and the physical space, and why they have a special address mode for stacks and local memory, because they automatically get then coalescing by interleaving the thread index then in a very implicit way, which is, I think, nice. Okay, so yeah, and I just want to say this local GPU memory threads live in a parallel universe, right? Where they can't address each other's memory, but in the physical memory, they're interleaved and give high speed, right? Because the thread index moved into the physical address bits in a way that makes them contiguous. Okay, so again, this fast load stores to local memory, stack's done in the same way. Yeah, instead of the local, if you have this shift, the relative address, and you stick the thread ID in the physical address used to index the SRAMs or the memory, that thread ID automatically moves consecutively, right? So when they all access the same word, you get coalescing this local memory. So it automatically interleaves local memory to if the threads are doing the same thing. So we've got these two models for SIMD and SIMT. How do we manage this? So this is what I call covariant programming. So almost all of computer science talks about portability and performance portability. by trying to make the program invariant with the architecture. And that's what they call portability. And my point here is that the right answer depends on the architecture. So the right thing to do is to make it covariant with the architecture rather than invariant, right? There's no single solution that works everywhere. So you have to come up with something that captures the differences and exposes them in a controllable way. So scalar codes, traditional CPU just needs, standard structs with lots of little scalars and a struct calculation. We introduced SIMD vectorization, where the CPU is really what people for a while were calling structive array optimizations, where you have vectors that are automatically vectors with some useful vector index that you're exploiting, but then create structures like SU3 of these out vectors. You would do maybe, for example, take part of the X dimension. If the vector length is 4, take 4 sides of the X dimension, lay them out as the 0, 0 element of this SU3 matrix, then the next vector is the 0, 1 element, etc., right? So you create a structive array transformation. That structive array transformation would depend on the vector length, right? SIMT coalescing, what you really need for read coalescing, what you really need is that the structive array to exist in memory, but each thread is accessing struct data, and the parallel threads next to them in the processor unit are accessing the corresponding elements of their corresponding elements of the same vector in memory. So you have this transformation between a structive array in memory to a scalar struct in the local stack of each thread in the GPU. So the way I handle this in Grid, so you have this memory layout and the optimal thread layout. The way I program it portably is to use operator bracket, square parentheses, square bracket, to transform the memory layout to per thread layout. On scalar and on SIMD, that's the identity map, right? But on SIMT, that's a non-trivial mapping function, right? Where you go from vectorized structive array to just structive scalar. And what I do then is I make the return type of this operator depend on the architecture with an if-def, right? Essentially. And the rest of the code is then parameterized. So with C++11, they introduced this auto and decal type, where you can ask, what type does this return? I want to declare a new variable with the type of whatever this would have returned if I had called it, right? And then syntactically, I can have all my local variables inside Grid in the key performance kernels transform the types of the variables that are living on their stack of local variables according to the architecture, and that's triggered by using the return type of this operator parentheses. Like there's a relatively elegant way, I think, to capture the distance SIMT and SIMT, with the result that I can write single kernels with either template parameters or whatever that are running optimally both in GPU and in CPU. They just use the return type of this to transform what they're doing accordingly. And then coalesce right. I have a coalesce right that I have to use. I couldn't find a clean syntax to avoid modifying the code completely. So I went to a complete rewrite of Grid for GPU. Here I use these stencil entries. This SE is a stencil entry, right? And ST is standing for a stencil object. What this is an integer table saying for this lattice site, where are the neighbors in plus X minus X plus Y minus Y plus X minus Z, etc. Right? So it uses this integer table when you create a stencil object, and the Fermion objects all use stencil objects. It just creates a list for each lattice site of where are the neighbors. These neighbors either live within the array or in an MPI distributed code that might come from a communication buffer, right? Which you've received. So the stencil knows how to do the halo exchange for a given geometry. So the idea is that basically the stencil knows geometrically what is the connectivity of this differential operator, and knows nothing about the coefficients or the internal indices of the objects that you're applying to. The mathematics, so the internal index algebra is handled external to the stencil. It just knows geometrically, given a stencil operating on type X, how do I gather things from different lattice sites, move them around, and make them available, and give me the information as to how to index them. Then the details of, does this have a Dirac index, does it need a spinner matrix, etc. The user of the stencil has to provide that, right? You then define the, sort of, I've separated the concepts into the geometry of the stencil versus the internal indexing of whether it's got gauge links and stuff like that that are needed to evaluate or apply the differential operator. This here is a generic stencil leg that's using the stencil that's pre-created to do the indexing. So basically that SE arrow is local, says, did my neighboring site in the X direction say come from on my node or off the node? If it's from on the node, it basically reads it in with this coalesce read permute. The permute handles the thing of if it came from different memory banks in the case of the connection machine, or if it comes from different SIMD lanes. In the case of my code design, you might have to swap the data around in order to get the data that came from the neighbor cell, right? It then does spin project. If it came from off the node, wise people with Wilson spin project before they send the data, because spin projecting cuts the data down by a factor of 2, right? So when it comes from off the node, you don't have to spin project, you just read it because it's already spin projected, right? And then you get this result into this variable chi, which you multiply by the gauge link and add to the result vector that you're accumulating. You just have this inside a loop over x plus y plus z plus t plus da 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 all the way through, and then you have the entire Wilson operator. So this is low-level code. I think about 2 people, maybe only 1 people writing grid have edited this code. And maybe one of them might even have occasionally edited it successfully, right? So I'm showing you how this works. I'm not necessarily saying anyone should be expected to program at this low level when they face grid, right? But I am trying to show that I'm using the decal type of coalesce read to define what I calculate on my stack, right? And then I have a macro which is just simply repeated and loops over the different spin projectors and the different directions and adds up terms and accumulates them, right? And the point being here also, we avoid thread divergence because there was an if and then there was an else. Some of them will go if and some of them will go else. You have to call an accelerator synchronize to say, complete both of these before you return. Don't split off and have double execution of things thereafter. So this guarantees you get back to the vectorized single execution at the end. The other interesting thing is I've followed something that's called C++ geeks call policy-based design. What this means is you pass in template parameters to a function where the template parameters contain knowledge of how to do certain things, right? And here, so I almost follow policy-based design. Mult-link is passed in as a template, it's a function defined by a template parameter called impl, the implementation, right? Which means that the same code works for both G parity and C star, or G parity C star boundary conditions, but there's an extra flavor index, and for the normal periodic boundary condition code. Which is kind of cute. So there's a single source for both G parity and non-G parity for how you do the Wilson operator. And this method, as I say, contrasts to most portability approaches where the software is tried to be forced to be invariant. This is actually deliberately changing with the architecture, what it's doing. Okay, so that's probably all on so much as unique in this. So I said GPUs hate branchy code. The thread enable mask is important. If some go else, then you have to make sure that we combine after you've executed this divergent stream. That's what accelerator synchronize was for. A program can be thought of as a binary tree of branch decisions. And if it's not regular and they're not all doing the same thing, you will rapidly fall down to running serial code on a supposedly parallel architecture that is really, really bad at serial execution, right? So unless you're exploiting the parallelism in a way where there's regularity, it becomes very difficult. This is bad news for HEP processing code like JONT, etc., right? They've got a really hard problem. Added to the obvious problems that virtual pointers don't work in the GPU, right? For example, right? So there's lots of, of course, they make references to V tables that live in the host. Okay, yeah, as I said, GPU register files are huge. That allows to schedule those early and cover latency. Many threads share the same execution types. Yeah, I can't remember. Here. Yeah, oh, and the other thing that's worth saying, GPU register files are multi-banked, which means that they have multiplexers down, so there are many banks, and you have to multiplex coming back up, which means that if you're accessing register 16 and 17 or consecutive registers, nearby registers, you get better performance than if you're accessing registers all over the place. So they have huge register files, but there's a penalty for that makes the code, the compiler challenge harder for them. The combination rules that only the compiler really handles well. Okay, so yeah. Then the idea is how to target these highly parallel hardware. And this is where I'm talking about my package grid. This is easiest if the syntax is high level and then broken down under an interface, right? So you're writing loops that have myriad loops and then recognizing which are essentially sequential, and then recognizing from that sequential loop that actually could have done all of this in parallel is much harder than having an interface where you say, do all of this in parallel and I don't care how, right? And I've seen people doing things with unified parallel C, for example, where they work for years recognizing that a loop over all the elements individually of the face of an array, accessing the neighboring node, reading it element by element, and writing a compiler that recognizes that idiom and says, aha, I can collect it all and send one MPI packet with every element, right? So they're going from this highly entropic state where there's all these individual scalar operations being defined by the programmer and recognizing just send the bytes, right? The programming interface is much better if they do all of this and you figure out how, and then you can make different rules for how you break it down into the little atomistic things that are required or as granular. So specify a large level of granularity and break it down if you have to. And if you can say, program a DMA engine that, get one word at a time and recognizing from that interface that you have to instead program a DMA engine to send it all. It's much harder than just exposing an interface that makes it easy to program the DMA engines in the beginning, right? For example, DMA meaning direct memory access. Okay, so I borrowed in concepts from the connection machine. I've got a link to a wonderful essay about Feynman's rule by Danny Hillis, who's also a famous computer scientist. Okay, so we deal with high-level data parallelism. We treat a distributed array in the programming interface that's spread across a multi-node computer as a single aggregate object, essentially. You can do linear combinations on them, multiply it by an operator, whatever, but the programmer just sees this as a single object and just deals with the object in a natural way. Handling the communications for the most part is just saying shift by 1 in the X direction, shift by 2 in the X direction, whatever, etc. This we have a where else, a where type ternary operator, which allows you to do things like F90 syntax type array slicing and wildcarding, or do this in everything when X equals 0, otherwise do nothing, right? Sorts of things. This is we have called predicated, so conditional data parallel execution is how you deal with side-by-side variation in a parallel language. High performance Fortran was worked on very hard in the early 2000s, late 90s, and was a failure effectively due to MPI latency. So they wanted to take this effective connection machine Fortran CM Fortran interface and port it to these message passing supercomputers. And they had, even when they were given the high level primitive of C#, etc., they still weren't efficient, right, in terms of the compiler implementations that they produced. largely due to MPI latency, but also if you have a series of things, if you're calling C shift in X, Y, Z, and T, positive and negative directions, you want to overlap all of that with each other concurrently instead of doing them one at a time. So the interface for HPF is still kind of wrong because your C shift this, C shift that, and it's coding one at a time. So to work around, so to try to not fail with grid the way HPF failed, the aim was to introduce dedicated objects for constructing fermion operators, especially, right? Do the slow C shift thing most of the time, but when you're dealing with a fermion operator, create the stencil that knows how to do an efficient halo exchange. That's all it really knows how to do, right? And which is why I have the separation of stencils for the fermion objects, everything else is C shift. Yep.
Is this failure lattice specific? Because like I know there are certainly like the fluids people love Fortran, right?
Mhm.
So like
For Fortran, yeah, absolutely, but not HPF. High performance Fortran is data parallel Fortran, where they had, like Chroma has, C shift, etc.
yeah, okay.
Right, so their HPF is a dead language, whereas Fortran is still alive. And, you know, Fortran will be alive at the heat death of the universe.
It's always 77.
The final step of the universe will be a go to zero. Sorry. So yeah, so we use these C++ opaque containers. We learned all the lessons we could from, you know, all of the expression template guys like Velthusen and so on. We have an expression template engine in Grid. You know, C++ 11, I'm relatively proud of this. We have about a 200 line of code expression template engine in Grid that is enabled by C++ 11. QDP++, for example, was written before 2011, right? That using C++NT, the language features then weren't there to write an ET, so we use this thing called PEAT, the code for expression template engine that generates something like 100,000 lines of code for all of the combinations of matrix times vector, matrix times matrix, etc. in each of the combinations, spin, color, something else, I can't remember, right? But it blows up to about 100,000 lines of code of expression closures. Whereas Grid has index by index the rules for matrix vector, as a multiplication table in it. Metaprogramming infers the nested indices cases out of it instead of having to enumerate them all, which is kind of fun. It's maybe irrelevant if you're using it, right? You know, they both just work, right? Okay, so, and we support CPU with SIMD across a range of architectures, CUDA, SYCL, 2020, and HIP compilation targets. And the whole point is you can do things like, you know, a legal statements A equals B star C plus C shift of D in the X direction by 1, for example. You can do pick a variable, a predicate variable with modular arithmetic. So this is something we use in EDHMC, for example, or actually I used this in the multigrid operator calculation. And you can use a where statement, where face is equal to 1, take this, else that, right? For example. Okay. So unifying CPU and GPU. So if you think about doing matrix times vector and ask how do you vectorize this, right? If you're doing vector operations, so even if you've laid it out right, so you have vector times vector, but you're doing matrix times vector, you have a reduction, right? And each of these multiplies involved, you know, the reduction across the results of these, you multiply one vector by another vector, element by element, but you still have to do some kind of reduction along the vector, which is going to be a bottleneck. You're serializing with a bottleneck. So the big realization of Grid is that if you have many vector sets, many matrices, and you turn the element, you know, this direction to move consecutively, then you automatically vectorize many vector sets, many matrices at the same time, right? And there's no serialization there, so you get 100% SIMD efficiency. So we both need in memory layout this kind of layout. So we make this transformation for both architectures, and it's optimal in both architectures. It's just the view seen within the computational thread. So the variables absolutely loaded from memory become stable in the GPU, thread, and the main vector is the CPU thread. So it's coalescing is working. And as I said, we over decompose the node then to create, we have this translational invariance. We know in the lattice, there's no reason, and it's kind of obvious when you think about it. We have many nodes in an MPI job, all doing the same thing as each other at the same time. And then we sit here and scratch our heads saying, why can't we vector this in a way where we have many things doing the same thing at the same time as each other, right? The obvious thing to do is just to pretend there are more MPI nodes than there are, but treat that little virtual node that you're subdivided by as the vector index, right? And then you have many things that are automatically independent and parallel, except for when you communicate between nodes, right? And that's essentially the trick, right? So I subdivide and then into virtual nodes that are small, nx smaller than the actual physical node, then write the code as if it's single node code for a word that is n times bigger. And then you automatically do the work of n nodes, right? And then only when you do the communications do you have to worry about whether there's any complexity there. Here's what I do. Okay, so then this is how we hide it. So portability 101, you use an internal abstraction. So we have d-dimensional lattice containers. These have an opaque layout. You don't get to see the transformation. You're not allowed to peek, right, if you're using the interface as intended, and have this partial layout transformation that depends on the architecture. There's a special template engine, the C shift, that allows us to write high-level code for the most part. I have an internal offload API in something I call accelerator.h. It's got an accelerator for that captures a macro. That macro has a variadic macro, has a ... in it. That captures a loop body and applies it, right? And it wraps around it with whatever gobbledygook you need to have, whether it's sickle, HIP, CUDA, or OpenMP to run it in parallel, right? It captures it in something called a C++ within lambda function. Doesn't really matter what it is, except for the fact that it automatically captures its arguments. You don't have to list the arguments to it. It says, I refer to this variable. I'll make that implicitly an argument to this function. So the nice thing is that you do not have to enumerate everything that's captured in. You have to make sure it only captures device pointers, for example. So quite often it'll be translation steps. If you have a container, like a device vector container, you can't capture the device vector container. You have to make a pointer to the first element of the vector. So take an ampersand of the element 0 and capture the pointer, and then you just get a plain device pointer coming in, for example. And we have accelerated copies of device, from device, all that sort of stuff. Grid doesn't have the users doing explicit device memory, host memory. For by far and away the most part, we have a automatically managed software cache. When you open, you can't dereference a lattice object. You have to get a view to a lattice shared with COCOS and other things. You have to obtain a view to the lattice object, right? And you can dereference the view in a kernel, whether it's a host side kernel or device side kernel. The process of getting the view, you declare your intent. You say, I want to access this on the device and I'm going to write it. I want to access this in the host and I'm going to read it. Oh, the device just wrote it. Oh, move it across, right? So it maintains a state table in something called the memory manager that says, I know where this basic object's unique identifier lives with its primary copy. Is it CPU dirty? Is it host dirty? Or is it consistent between the two? Or is it simply not present on the device? So it's a software managed cache. It's a state table. The state table is a hash table, which means the cost of accessing it doesn't grow with the number of items in the table. There's a true, least recently used queue, where when you open something and then close it again for access, it gets put on one end of the least recently used queue, the front. When it needs to evict something to make space for something on the device, when it's going to move something in again, it takes from the tail of the queue. So really, the least recently used thing is always at the tail, because it was the thing that was earliest put in the queue, and everything else is put in front as it comes, right? So the access to that is as a standard double linked list, using standard C++. Putting something in the front, putting something in the back is free, order one. Removing something in the middle, it's a double linked list. I've got a reference to it. You just make something in a chain, stitch together, right? It's order one removal. So I maintain true LRU and software managed cache table with order one cost access. It doesn't grow as the GPU memory gets bigger or the number of benches grows. So we've got CPU dirty accelerator dirty consistent. And open a view for GPU. Your GPU's got reference count for reference count for the device, reference count for the host, increments when you're opening things, and then you can't open on the CPU if it's open on the GPU and vice versa. That's a programming error, and it will flag it and tell you, right? The API covers OpenMP, HIP, cycle, CUDA. You don't see it. It's all under the hood. I've wrapped it. Vector intrinsics for most CPUs and most major GPUs. The users do not see this API because it's hidden under the expression template engine for the most part. So hadrons, for example, the contract with hadrons is you will not drop beneath this higher level. We will write things in grid if it's doing it because then I can maintain it, and if I change the interface, they will not be broken by it. The API so most users don't see it. The API has been used already by Christoph, Chris Kelly. Liu Chang used it. Actually, Liu Chang used it, but I think he took a copy of it, modified it, and so on, right? So this is open source, right? As long as you keep GPL and you're happy with that, you can use it, right? So it's been used and taken, used in various forms, right? This is kind of, if you want a compressed 200 or 300 lines of code of how to use GPUs and use them effectively, look at it. There's a guy, Timo Eichhorn in, I think, Wuppertal, looked at grid, liked it, and one of the most complimentary things I've had to say to me is, you inspired me to write my own code base, right? Using the same programming techniques and stuff like that. I like people programming, right? You should, it's part of the skills of the job, right? So, so it's open source. Don't give me mind for ideas. Feel free to steal. And I think at that point we started. Yeah, I'm an hour and a half. Yeah, we're kind of out of time. So I'll return to this.
So really interesting talk. This might be a bit too technical, but so you were talking about the stencil for the Wilson operator, and you said kind of there's a lookup table that stores like the neighbors at each of the sites.
Yeah.
And so, okay, so to then compute the stencil, it's like an indirect access because first you have to look up where the site is, and you have to look up the actual site. And I'm thinking, okay, if you have a lattice that's kind of regularly laid out in memory, like X runs fastest than Y than Z, you could kind of compute these indices on the fly.
Yeah.
Is it a performance penalty to have to do this kind of indirect lookup?
Yes, there is potentially. I think on most architectures, the overhead of redoing the calculation, GPUs don't have an integer divide. Power of two divides are a lot easier than non-power of two divides, etc. You'd start. So I do think that the overhead of recalculating it on the fly would exceed the overhead of doing a fetch. Even if you are willing to, I'm not willing to compile time fix the lattice block, right? So therefore, you will still have to go and fetch what are the lattice dimensions and do a calculation. So still a dependent load there where you can't do the calculation of the neighbor until you've done a fetch, right? In some sense. So I don't think that I'm losing that much by dependent loads. But certainly dependent loads are evil, right?
Thank you so much. That's very helpful.